All right, moving through the homework 7 key. Finally, a magnetism problem. This is going to be the bulk of the upcoming test. Magnetism. Okay, last thing was devices. This one we have a magnetic field. It was just given to us that we have this conglomeration of things in cylindrical coordinates. And the question is, on problem 2, what is the total current through a 10 centimeter radius loop? There's a few more details, like the loop is at the center, and it's in the z equals 0 plane, and we have this crazy field, and it's really an Ampere's law. Big, big deal for this test. H dot dl equals I enclosed. And we're asking, what's the total current going through this loop due to this external magnetic field? Okay, and this loop it doesn't necessarily have to be a wire. It could be just an imaginary boundary defined here and kind of do the math. Okay, so we've got something. Can anyone tell me what DL is? I'm not going to be able to hear you, but we should look on our equation sheet, and it's going to be rho d phi if we're going around the edge of this circle. Okay, 0.1 meter radius, and what's missing? I have a direction on it. Phi hat always goes kind of around from the x equals, well, the positive x-axis going towards the y-axis, and then this is your z. Okay, so we've got that, and when you see that, it's just kind of plug and chug. Phi starts at 0, he goes to 2 pi. Shouldn't really matter where we start and end, but we have to go all the way around and then drop in this thing. 3 rho sine squared phi. Phi hat. Put all that stuff together, do the dot product, and evaluate it at 0.1 meter. Okay, we've got rid of all the unknowns here. So you go through the key and you see that. Why I want to belabor this key, or this thing beyond what's on the key, is Ampere's law type problems often can be looked at from two different perspectives. It's really a Stokes' theorem problem in disguise. Okay, because we could take this apart. We can go I is, so also going beyond what's on the key. This little side area here, I is J dot ds. I got a little bit more room over here for some graffiti. I can compare these two things. I can go, well, H dot dl is going to be curl of H dot ds. And that is really a statement that these two things have got to be equal. J is the curl of H. We're not really doing a problem right now. We're kind of rewriting Ampere's law in differential form. I usually write J on the other side. If you get the t-shirt, it's got the operators usually on the left side and the sources on the right side. Ampere's law, differential form. Okay, what's the big deal about that as a source of test problems? Okay, there's really two ways to find the total current. Okay, you could do this and do a nice path integral, or you could take the curl of this thing and integrate it over a surface. If you'd rather do a surface integral, okay, could do curl of this thing, and this is something you could just try out if you really want to get a good test review workout. Take the curl of H, plug it in to your stuff in the equation sheet, and then remember what we're doing here is J dot ds. Okay, we're getting J by doing this. We have to plug in ds. Okay, when we're in cylindrical, ds is these little things like rho, d, v, and d rho. Okay, going out along rho, going around and phi, you got to scale it by rho. So we have to drop in our ds. So you see how you're getting a little bit of everything when you solve this. And what you should come up with is the same same result for the total current as you got in the answer key for homework 7. I think that would be a real smart thing to review. Okay, J.ds. Let's plug in ds. Rho, d. I'm not picky about what order you cram it all in, but remember it's got a z surface normal. Okay, this is mind-blowing because when we do the ds, we know we're just going to have to get the z part of the curl. It's a very common shortcut. Okay, and we also have to plop in the right limits. Okay, rho is now going to go from 0.1 meter, and phi is still going all the way around. Z is going to be stuck at 0, doesn't really matter. Okay, and phi equals 0 to 2 pi. So you got all the ingredients for a kind of a tour of every possible iteration of these Ampere's Law type problems in cylindrical coordinates. If you do this extra stuff and just check and convince yourself that you're getting the same answer for I with this method, you know, the J dot ds, getting J from here, and then using that thing. Long way to go, but you could be asked to do such a thing on the test.